Hello, I'm Tae Kang. I will introduce our work Attention-Propagation Network for Egocentric Heatmap to 3D pose lifting. The Egocentric setup is gaining attention for VR applications. The setup uses cameras on the head, such as one mounted on the HMD devices. Without external sensors, Egocentric setup provides an unobtrusive experience. We introduce methods to improve pose estimation from Egocentric cameras. In many applications, users express themselves through pose reflected on their avatars. Images on the right show egocentric camera views. In egocentric view, body parts are occluded or out of the view, making it challenging to estimate full body pose. To deal with the ambiguity from the limited view, many methods adopted Heatmap, a probabilistic pose representation, as an intermediate output. The 2D pose in a form of Heatmap is lifted to 3D pose, utilizing a network that takes features from all joints. In this previous approach, feature extraction used the CNN encoder, taking heatmaps as multiple channels. However, spatial locality assumption of CNN does not hold. Neighbor joints are often distant in pixel, and features cannot be combined by early convolutional layers. This inefficiency leads to loss of information, indicated by the lossy reconstruction of heatmap from the extracted features. The CNN encoder also ignores heatmap and joint correspondence, treating different heatmaps as channels. Furthermore, they do not distinguish important features. The image shows deviation of estimated pose of left arm, despite the clear 2D pose captured by heatmaps from stereo views. Impacted by the obscure joint features, visible joint pose estimation can be inaccurate. Egotap architecture tackles the challenge with grid vision transformer encoder and propagation network. Egotap takes limb heatmaps and joint heatmaps. The grid vision transformer encoder takes joint heatmaps and generates effective feature embedding corresponding to each joint. The propagation network processes these joint features with their relational information. With the awareness of the skeletal structure, it takes advantage of the parent joint features to improve child joint pose estimation result. Heatmap is a probabilistic pose representation. Our method takes two types of heatmaps. Joint heatmap represents 2D pose of each joint. Limb heatmap represents 3D relationship between joints. The joint heatmap is processed by the grid vision transformer encoder, and limb heatmap is processed by a MLP encoder. This processed feature is utilized by the propagation network layer. Our grid vision transformer encoder places all heatmaps in a grid to make one image and encode it with attention. Attention is applied globally across different heatmaps and their patches, enabling features to be combined in early stages. Heatmap patches and output features have correspondence. We separate features for each joint by aggregating heatmap patch features that correspond to each joint. In the egocentric view, parent joints are close to the cameras and have more evident visual. Parent joint features and the relational information from limb that connects to joints can be utilized to estimate the child joint pose indirectly. Stage from parent joint is processed with a LSTM-inspired propagation unit. Encoded limb and joint heatmap features are taken by the PU cell to update state from the parent joint. The output propagated feature for each joint is used for estimating the final pose. The PU prevents adverse impact from parent when child joint has evident visual. It selectively forgets the parent feature based on the child's feature. Our method outperforms previous methods in all motion categories in the Unreal Ego dataset. It reduces joint position error by 23.9% MPJPE and 17.7% PA-MPJPE. On the EgoCap dataset, our method outperforms previous methods by 22.6% in MPJPE and 9.4% in PA-MPJPE. Experiments demonstrated that the grid vision transformer encoder improves the pose estimation result by 22.8%. Output feature better preserves the heatmap information, reducing heatmap reconstruction error from features by more than 6 times. The propagation network improves pose estimation by 14.7%. We further analyzed if the network actually takes advantage of parent joints feature to improve child joint pose estimation. We used propagation potential and propagation effect, approximating the expected and observed benefit from the feature propagation. The expected and actual benefits from propagation have positive correlation. It is especially evident on the camera-relative pose estimation on the unreliable dataset, where the camera setup is similar to the HMD device-mounted setup. From the project website, you can access our released code and paper for details. Thank you for watching.